Oh, hello there. Today I will talk a bit about this balancing robot. It's a new version, and basically, what I'm trying to do is to make a version that is just as cute and just as nice in terms of behavior, but is cheaper compared to the previous version. The previous version uses stepper motors, which are relatively heavy and expensive, and by using DC motors, as you can see here, I'm trying to make the robot much cheaper. A friend made this very nice design for the frame and also 3D printed it, so it can be 3D printed. And the nice thing here is that the motors are directly connected to the wheel by means of an internal gear. So here we have a big ring gear and a small pinion gear. Now the ring gear is internal because of some advice that another friend gave me. Now the rotation direction of the motors is the same as the rotation direction of the wheel. And this is useful because I want the robot to be able to self-right. So basically if it's lying down like this, it should be able to self-right. At the moment it's not able to do that, but it will be able to do so later on, like the existing robot. And to do so, if the rotation direction of the motor and the wheel are the same, the inertia, the moment of inertia of the motor will help in the self-righting. And because we use a DC motor with a relatively large gear ratio, the motor moment of inertia is much more significant compared to the stepper motor version. So this is a neat trick. So here I've added some friction compensation. So basically I just add a small amount of PWM duty cycle to the output of the controller, multiplied by the sine of the output. So this works, and you can see that the robot now doesn't have this rotation issue, but it starts shaking because the friction compensation is very crappy, because friction is hard to predict. Yeah, but it works. I mean, it's not optimal, but this very cheap balancing robot now is actually balancing. So, no, I think for a first prototype, or rather a second prototype, it's yeah, quite a nice result. Right, if you have any good ideas on how to solve this or further improvements for the robot, let me know. Okay, a small addition that I forgot to mention. Stepper motors continuously dissipate power, so they are not energy efficient. And DC motors only dissipate power when you tell them to do so. And this has the advantage of minimizing the needed current. Here I'm using the power supply, lab power supply, to power the robot. If I move it around a little bit, the current draw is about 0.2 amps. Now the idea for this robot is to use one single lithium 18650 cell, which typically has a capacity of between 2 and 3 amp hours. So that means that with just one single cheap battery we can operate this robot for 10 hours, which is insane. So, added bonus. And an additional thought on the friction compensation. So the reason why the friction compensation is, so it's very jittery, but it works. So it's continuously shaking, so it's always having some movement, so the robot will never get stuck in friction. So it's a dirty way to solve the problem, and it will also be inefficient because it will consume a lot of power. But yeah, it's a solution. Well, that's it for today. Thanks for watching.